All right, in this video we're going to talk about the geometric distribution. So again, recall that a Bernoulli trial is a trial with exactly two outcomes. Okay? And remember, exactly two outcomes. We called one of those outcomes a success and the other a failure. We denoted the probability of success P and the probability of failure 1 minus P. Okay? When we looked at the binomial distribution, we completed a fixed number of identical independent Bernoulli trials. And in this scenario, we are going to perform independent identical Bernoulli trials until, and that's the key word here, we achieve the first success. Okay? So we are still performing independent Bernoulli trials that are identical, but this time we're not doing it a fixed number of time. We're doing it until we achieve the first success. Okay, so this does not have a fixed number of trials. Okay, and we're going to, instead of, if you remember in the binomial distribution, our random variable x counted the number of successes in a fixed number of trial. Here, we're going to let x count the number of trials needed to achieve the first success. Okay, needed to achieve the first success. So for example, you're going to flip a coin until you get a heads, or you're going to roll a die until you get a 6. Okay, you're going to stop once you've achieved that success. All right, so that means x can't take on the value 0 here because you can't achieve a success without performing a trial. So the smallest value it can take on is 1, which means you achieve that success on the first trial. 2 means it takes you 2, 3, and so on. This time we don't have a fixed number of trials, and in fact, we can go on and on and on and on. We might keep flipping a coin for decades and not getting a heads. Not likely, but we could. Okay, so let's now see if we can construct, we see again that x is a discrete random variable. It is not finite like with the binomial, but it is countable, enumerable. It is a discrete random variable. Again, that means sums are involved, not integrals. Just like before, we want to be able to find the probability mass function. Because it's discrete, we should be able to find the expected value, that is the mean, and we should be able to talk about the variance of our random variable x. All right? So we're going to construct this like we did before. So remember, x can take on the value 1, 2, and up forever. So what does it mean for x to be equal to 1? Well, that means that you get a success on the first trial. And the probability of success, so the probability x equals 1, is exactly p. Okay? What about x equals 2? Well, this means you have 2 slots, but you can't choose where the success goes because it can't go in the first slot, otherwise you would be back into case 1. So what happens here is failure and then success. And that's with probability 1 minus p times p. Okay? If I say x equals 3, well, that means failure, failure, success. The only way we get 3 is if our success is on the last trial. So that means 1 minus p squared times p. Right? What if I said the probability x equals 10? Well, that means I have 9 failures. So 1 minus p to the 9th, and then the last one is success. Okay, let's generalize. What if I say the probability x equals k? That is, it takes k trials to achieve that first success. That means I have k minus 1, so 1 less than k failures, and then the last one is a success. All right, this is the probability mass function, the PMF, for a geometric random variable whose probability of success is p. Okay? Also, the expected value of x in this particular random variable whose probability of success is p is 1 over p, and the variance of x is 1 minus p over p squared. This means the standard deviation of x is the square root of 1 minus p over